machinery and equipment valuation. And our presenter is going to be Mr. Bavik Vora. He's an associate director and manager, and manages the Dubai office of RBSA Advisors. He is actively involved in business development and leads asset valuation and technical advisory mandates. He has more than 15 years of professional experience and is associated with the firm since 2008. Mr. Vora has a rich experience in real estate valuation, industrial assets, including plant and machinery valuation, and technical due diligence. He is based in UAE and is involved in valuation and advisory assignments across India, UAE, and Middle East region. He is a mechanical engineer and has a postgraduate diploma in business administration. He is an accredited member of American Society of Appraisers and an associate member of Royal Institution of Chartered Surveyors, RICS. And he is a certified real estate valuer registered with RERA in Dubai and Abu Dhabi. He is also trained SAP MP modular implementation, Six Sigma initiatives, and internal auditor for International Organization for Standardization. Ladies and gentlemen, I hand you over to Mr. Bavik Vora to do the presentation. Over to you, Mr. Vora.
Yeah, thank you so much, Ruka, for the kind introduction. Appreciate. And thank you so much, everyone, for taking your time out to be present in this training session. So the topic of this training session is, as you're aware, it's a life cycle analysis of machinery and equipment, and focusing more, how we can use this, in our, valuation practice. So that's the idea of whole, this training session, right? So before we go more, depth into that, analysis specific to the valuation, would be more talking about what actually the life cycle analysis is, right? When we say a life cycle analysis, it's a wider subject, right? And applied to the various disciplines, right? Not only in the valuation, right? So I would be talking initially, what the life cycle analysis is, and then, we'll take to the, how the life cycle analysis can be, used in the valuation, perspective, right? Yeah. Yeah, so the life cycle analysis, it's a process of assessing and documenting machinery and equipment impact on the users and the environment. That's the broader, I would say the concept. And we have shown the areas which it has an impact. The impact of the life cycle study. It can be on the energy efficiency of the machinery, where we are more focused nowadays. Natural resources, what kind of resources the machinery is going to use, the planning, the regulatory compliance with the health and safety requirement, environment, the economic performance. So there are many factors when we do a life cycle analysis, and it has an impact on the many areas when we do a life cycle analysis of any machinery and equipment, right? So these are the broad, the major areas normally which are covered in a life cycle analysis of the machinery and equipment, right? Whenever we do any procurement, or when we are thinking of to install any machinery, there are so many areas we need to consider in a lifespan of any equipment when we are going to use it, right? Now, what is the concept of life cycle analysis, right? And, basically, these are the wider, we are talking of a wider concept, right? So an asset life cycle is the process by which, the companies first the purchase, then they utilize, monitor, maintain, and replace or, dispose the asset, right? So it starts from the procurement first. When we call a life cycle, the life cycle starts itself from the planning or procurement. Then once it's procured, once it's installed, how we are going to utilize and monitor it, how we are going to maintain it. And then at the end of your life, how we are going to replace this or, dispose of the given asset. The asset life cycle management allows to optimize asset useful lives, and that can be done through the planning and the maintenance to increase the productivity, maximize the asset life, and reduce the cost. At the end, all this planning will help to maximize the economic benefit given by the machinery and the equipment, right? So that's the whole concept of doing the life cycle analysis. At the end of the day, we want to have a longer lifespan, better maintenance, and better economic benefits to reduce cost and the productivity. If we divide the whole concept of this analysis, it is into the three phases. First is the investment phase, right? Where it starts from the origination of the requirement, right? Why I need this machinery or the asset, right? Then the requirement goes to the procurement, right? And then the procurement goes to the details of the design, manufacturing, then and the transportation and the installation. So the first phase of any life cycle analysis, right, would be the investment phase. And that's the, a phase where, the company decides, procure, right, and install the machinery. Once the machinery is installed, right, the second, the phase of the analysis would be the operation and the maintenance, right? Now, operation and maintenance, these are basically a longer phase of analysis where most of the assets which are used, they are used normally, like ranging from 5 years to the 25, 30 years of life, right? When we are going to use this machinery for a longer period of time, certainly there are many angles which will have an impact on the economic outcome, right? When we use those assets. So operation and maintenance, how it is going to consume my powers, how it is going to be emit some kind of a gases, right? What are the maintenance requirements during the lifespan? What are the capex or major overhauling, requirements during the lifespan of the equipment? All these things are considered in the analysis because a lot of time, sometimes some machinery equipment are very efficient, but at the same time, it has a high maintenance cost. So any company or user certainly will have a, view on, whether it is going to make any economic sense to invest that much money or not, right? Because maybe the machinery at the, maybe at the initial procurement stage, it is, a cheap, but there are high overhead running costs also. So all this analysis, needs to be done when we do a complete life cycle analysis of any machinery and equipment. And the third and the last phase of the analysis is the decommissioning or disposal of the equipment. Now, a lot of time, many plant and machinery or something, or some kind of mining equipment in a mining industry, there are so much government regulations, right? And there are some disposal requirement norms needs to be followed, right? And all these things of during the lifespan, if there is some kind of a pollution it has created, then there is some end of service liability also when we dispose of those kind of a machinery and equipment, right? So all these things needs to be considered when we do, whole life cycle analysis. See, we are talking about right now a larger, a concept of the life cycle analysis, right? And there are the three phases where, whole analysis is involved. So as we discussed, it would be investment phase. It would be, which would be maybe, 6 months or 1 year of time, normally that would be the phase will last. Then the operation and the maintenance, which would be ranging from 5 years to say 25 or 30 years of lifespan, right? Depending upon the life of the useful life of the machinery. And the third would be the decommissioning or end of life disposal, right? That's the last phase, maybe a 6 month or maybe a 1 year, depending upon the machinery or plant, how much time we need to, take the, decommissioning, right? So these are the three phases, which normally, when any person does a life cycle analysis, it will do in 3 phases, right? And yeah. Yeah, so we already, discussed this, when I spoke. So the investment phase, is, is the first phase, right? It starts from planning for the replacing or acquiring new piece of equipment, right? Basically, it can be for the new project, acquiring a new piece, or for existing, the plant, it can be a replacing of the equipment. After planning, equipment is procured, and, it would be transported and installed at the site, right? The second phase is the operation and the maintenance phase, right? Which is the longest stage of any equipment life cycle. Operation, mainly the purpose for which it is, intended to use. And the maintenance means carefully, it is the maintenance or, the capex or opex, whatever we do to support its, performance over the period of time, right? So that's the second phase. And the third is a decommissioning phase, right? That's the the final stage of equipment life cycle. So the final stage of equipment life cycle involves the proper disposing of the assets. This stage cannot be overlooked. As I discussed, can be many regulation, environmental impact when we remove the equipment or decommissioning the whole plant, right? So these are the 3 areas normally we look or the 3 phrases we review when we do the life cycle analysis, right? Now that was more about the analysis and its phases, right? And partially I also discussed some purpose, right? But we are going to discuss this more in detail, right? So what is the purpose of doing the life cycle analysis? Now, why we do this, right? Can we just have a best offer in place, right, and just buy the equipment and let's see, whatever happens, we'll see, or we should have a proper planning, because wherever this equipment or a plant we are going to be used, certainly those plants, equipments are used for some kind of economic benefit for the organization or the investor, right? So certainly when we do this life cycle analysis, there are some purposes, and all these purposes are related to increase the productivity, reduce the breakdown time or the breakdown maintenance, or increase the lifespan or utility of the equipment, or minimize the end of use liability or some kind of end of use cost while decommissioning of the equipment. So there are many benefits, there are purpose of doing all this analysis, right? Yeah. So, as I spoke earlier, see, machinery and equipment will not last forever, right? There is always certain life to each and every machinery. It starts from maybe 3-5 years to range from 25 to 30 years, like cement plant, power plants. So machinery and equipment will not last forever. it is important to have an understanding of where each asset resides within the cycle to avoid the unplanned asset downtime, right? So this is one of the advantage, if we know, the assets. You see, if I have a group of say a lathe machine. Now, these lathe machines are procured at a different point of time. Maybe one lathe machine is say procured 3 years ago. One lathe machine is say procured 5 years ago. So all these lathe machines have a different use, first of all, right? Now, maybe, sorry, these lathe machines are used for a different purpose. So they have a different utility also, right? So if I plan the maintenance properly, I know the utility level, everything, I avoid unplanned asset downtime, right? So these are the reason, we do all the analysis. This can help decide which equipment should be prioritized for the replacement and budget accordingly. So if there are lathe machines, maybe there is a lathe machine which is 10-year-old, but it was utilized for round the clock for 24 hours, right? And there is a machinery which is say 15-year-old, but it is not used as maybe only 8 hours a shift. So utility is different, but I need to prioritize the 10-year-old machinery, which is being used 24/7. Maybe I need to replace it immediately, or maybe in near future, as compared to a machinery which is a 15-year-old, right? But not utilized as frequently as the other machinery. So this will help me, which equipment should be prioritized for the replacement and the budget accordingly. And I can plan my budget accordingly, right? And the third point, every machinery and equipment goes through distinctive life cycle phases, right? And affecting its, value from its design to the end of use life. So certainly when we talk of, a larger plant, right, where we have a different, kind of a machinery, right? Every machinery has a different use. They are worked in a different environment. Some work in the, say, within the enclosed environment, some temperature control environment. Some machineries are exposed to the harsh environment, heat, wind, or some kind of a gas or something. So all the machineries are exposed to different environment. Again, even the similar machinery can have a different utilization level. They are procured at a different point of time, right? So all these things will affect their life, the maintenance cost, and many other things, the productivity. And all this will have at the end of the, will have its value, right? So if I want, some kind of a, because all the plant and machinery, these are the business assets, and they are procured, or they are used, or they are built to generate some kind of a, return, from that investments. So if I want to have a certain level of investments, right, or I have some expectation about certain return on my investment, certainly then I need to plan everything in advance, well in advance. So to achieve unplanned or to achieve that ROI from the investments. And that is the reason this has become a very important concept now, in like when in the plant and machinery, also the life cycle management or life cycle analysis. So when we do, the life cycle analysis, right? There are some, although some of the things we discussed earlier also, but this is again would be going one by one, right? Partly maybe I spoke earlier, but when we do a life cycle analysis, if there are the four major area which or the main for the purpose of doing this analysis. First, we define the assets, its conditions, right? The second, that it support a proactive approach to the maintenance, right? Third, support a regulatory compliance or some kind of regulations which are required by the local authorities. And it also helps us prioritize the equipment machinery replacements. So these are the four the main reason or the purpose we do the analysis. Now we are talking more on a wider subject in this life cycle analysis part, right? So the first thing, it enables to record the installation date, the condition, cost effectiveness of each equipment. This data can be used to forecast an asset's estimated useful life and the total cost of ownership, right? So when we have an existing equipment, right, and we know what when the equipment was installed, what was the cost, what was the maintenance cost, all these things will help when we procure the new equipment, we can estimate or forecast what would be the useful life of the machinery. And during this 20 years of life, how much would be the total cost of ownership, which can be the procurement cost, installation cost, the running cost, or some kind of a overhauling cost also, right? So that is the one purpose. The second the purpose would be the life cycle analysis is focused more on the proactive approach to the maintenance, right? Because the breakdown maintenance or any reactive maintenance is more costlier than any proactive or preventive maintenance. So asset life cycle management or analysis help to manage the physical health of the machinery. Proactive maintenance enables organizations to better predict future scenarios, plan for asset failures, take well-planned steps relating to the maintenance and the eventual future replacements. So this is the purpose, we do, all. Basically, it saves the unplanned expenses or, the downtime. That is the reason. The third, many times there are regulatory, compliance, say, when you have a boiler in place, it is emitting some kind of, gases or carbon dioxide, right? Or some kind of a chemical plant where, the gas is coming out of some of the scrubber or some kind of say a vessel. It has to be treated and the quality needs to be maintained, right? Of the, the gas coming out of the, any, chimney or, the vessel. And all this data needs to be monitored, and to be reported to the, the regulatory authority in the city or in the area where, it is operating. So by proper training of the team members, they can collect and utilize valuable life cycle data for each critical asset. This way, this team can be notified, to the existing problem. They become compliance if there are any compliance issues or, any agency needs to be, alerted or, reported. So this is also one area, where, when we do any analysis, how much carbon emission it is going to happen if we bring this machinery, whether it is permitted, not permitted, whether, the gas coming out of the plant or something, whether it's, meeting the requirements which is allowed as per the, the local and environmental authorities. So that is also one of the purpose we do, this analysis. And the last, you prioritize the replacement. So certainly if once we do the life cycle analysis, we know, what is the utilization level of the equipment, whether, if there is a high maintenance of, improving any machinery, whether it, makes sense or we need to replace the whole new machinery rather than going for the, any partial, repairs or overhauling, right? Or we need to, use any, maintenance reserves. So basically, creating and maintaining a capital budget is, an important part of any, or managing any equipment. So, by staying up to date on asset conditions, life expectancies, the funding needs and the maintenance reserves can be accurately forecasted. So basically, it helps us, accurately forecast what the cash we will need or the budget we need to make to maintain those, assets during their lifespan. Yeah. So as we discussed why we, do the life cycle analysis, what is life cycle analysis, what are its phases, then we came to the purpose, of the life cycle analysis. And then next comes, when we do a life cycle analysis, what are the benefits, right? So one of the main benefit I would say is, is to the extended, asset lifespan. Tracking an asset's life cycle offers a valuable information on how that asset operates, and maintenance is the most optimal. So this information can be used to create an asset life cycle plan, highlighting the base maintenance intervals and procedures to keep asset operating in its peak condition. By intervening, with the preventive maintenance at these critical points, one can extend, assets useful life. So basically, if we do a proper life cycle analysis, we are aware of where to do a preventive maintenance, when to do a proactive maintenance. This will, reduce the breakdown or reactive maintenance, requirement, and ultimately it will lead to a, better, or extended useful life of the machinery. Same is the second, benefit is the decrease in the downtime of the machinery. If we do a proper asset lifecycle management, it will reduce the need for reactive maintenance. Subsequently, it decrease the downtime, right? Planning, any maintenance before, the requirement, or, basically it's a preventive maintenance. It will, reduce the asset downtime, and, it will also reduce at the end of the, the cost also, because always, the reactive or breakdown maintenance are costlier than the preventive maintenance. Maintenance can be scheduled, and we can plan for the maintenance. There are many continuous process plant, right, where, we need to do a proper, planning to, do a preemptive maintenance, or if there is a breakdown maintenance, there is a long period to again restart the facility also. So it's not about downtime is only not related to the machinery itself if it fails, but sometimes it's a continuous process plan, then there are longer hours to restart the facility also. So that is, the benefit, the decreased downtime. This will also lead to a better, if there are, reduced maintenance, reduced downtime, or, extended, lifespan of the machinery, certain that will lead to a better operational efficiency, right? And so, and if the efficiency is better productivity, reduced, downtime, or the, the reduced cost, certainly it will have a cost saving. So better, in ROI we can generate through the cost savings. Ultimately, if the, the lifespan is longer, then, there is we can postpone the replacing the asset, or, purchasing a new asset. That's a saving. Decrease downtime ultimately, which means, there is a more time to produce the goods, or, or services that generates a more revenue for the firm, more profits for the firm. And that's the general, trend that, the reactive maintenance typically costs 3 to 9 times more than the preventive maintenance, right? So definitely there are huge motivation to do, preventive or proactive maintenance than, the reactive maintenance. And all these things also we can have an informed, decision make. This help us, making a informed decision about the, assets replacement, maintenance, or, decommissioning. So assets lifecycle management offer insights into the facility, which would, this knowledge can inform the decision making process and help better plans for the future. For example, when it comes to decision like repair or replacement, one have the financial data backup or we have a historical records, we have already done the analysis through which we can come to know which is the cost-effective solution. Now, what we talked so far, it was more, talking a wider, a subject about the life cycle analysis, right? And it was, talking more about, investor perspective also, how we can generate more, return to the investor, or, how we can, meet our, return expectation, and those are the, the areas we covered, the larger area we covered. Now, we are more talking about, how, this can help us in machinery and equipment valuation, right? So definitely, when we do, any evaluation, we value, any plant and machinery, we look at different areas. One of the areas, is the balanced useful life, right? Because when we value machinery, right, maybe, it's a 1-year-old machinery, maybe it's a 5-year-old machinery, or maybe it's a 15-year-old machinery. Some machineries are, in the last phase of their, life cycle, right? So, to value those machinery, one of the, key factor, which will have an impact, is the how much is the useful life, balanced useful life of the machinery, or balanced life of the machinery, right? So when we do, or estimate any, value, market value of the plant and machinery, depreciation estimation is a critical function, right, of all the organizations, both private, public, that maintain capital and thus depreciable equipment and the facilities. Now, determination of the probable service life of machinery and equipment at any age is critical, right? And it also allows, what is the life expectancy, of the machinery for the remaining useful life. So basically, life cycle analysis help us, estimate the balance, useful life, right? What is the probable useful life of the machinery when we have the age data, or we know, this is the age of machinery, or, this is the different age of different machinery. So life expectancy becomes the basis for the number of years used in the present worth calculation. So whenever we, do any, calculation for even for the estimation of the market value, or any, present worth calculation, we need to have a data. What is the balance, useful life of the machinery? What is the life expectancy of the machinery, right? And this basic measure of the value is the present worth of the future, returns. Life estimation techniques also provide the capability and continual reassessment of a probable average life, as machinery and equipment ages. Thus, annual depreciation as well as the depreciation reserve amounts, for example, can be monitored and adjusted as the machinery and equipment affected by economic obsolescence or varieties of, other changes or decisions that affect the probable average service life over the period of time. Life cycle analysis is used to assess the depreciation impacts of the forces of depreciation. This methodology allows the analysis to separately model individual class of depreciation using different modeling techniques appropriate for each class. It proposes that the analyst use traditional mortality analysis techniques like actuarial analysis to assess the influence of physical depreciation, ordinary obsolescence, and use other modeling techniques to assess the depreciation resulting from the abnormal functional or external obsolescence. Finally, utilize the life cycle techniques to represent and combine all the forces of depreciation obsolescence into a composite life cycle from which net depreciation or economic lives can be determined. So the idea, of a life cycle analysis on a, if we say a valuation perspective, is to assess or judge the depreciation impact of all forces of depreciation. Now, when we say all forces of depreciation, so there are mainly it can be a physical depreciation, it can be a technical depreciation, or it can be some kind of economic depreciation also. Now, when we do a life cycle analysis or when we do a survival analysis, we are focused more on a historical data, how that equipment have behaved over its lifeline. We study the different group of equipments, try to make a analysis like which equipment survive till what age, right? So some equipment survives 3 years, some equipment survive 5 years. So there is a set of data, right, which we review. And we try to make a complete life cycle or survival curve, and that curve can represent various forms of depreciation. It can be if we just purely focused on the equipment usage data, it can represent only a a physical depreciation trend of the machinery. If there are equipment which are retired because of some other factors, can be there were some more technologically advanced equipments has come up and the company has removed the obsolete equipment. So for example, there is a 3 sets of equipment. One is technically advanced, or it's a new equipment. There are other old equipments which are technically inferior and which reduces the the utility or the productivity of the productivity. Certainly those would be retired earlier, although they are physically capable to run, but they are not economically efficient or viable to run, and it can be retired or removed from the service earlier. So if we follow those kind of data and make a the life cycle analysis graph, this graph can represent 2 factors. It's not only represent the physical depreciation factor, it can also represent the technical obsolescence factor. So when we prepare a life cycle or survival curves, they cover various forces of depreciation or various kind of depreciation, right? So that is and this can be used in estimating the economic lives or the the depreciation to be detected from the current replacement cost new. Now, for all this survival curves, everything, they are basically based on the historical data, right? And for most of the last century, all the causes of depreciation were typically accessed collectively using actual studies, right? Where they observed the mortality patterns of the group of similar equipments, machinery, determined and represented in the form of survival curves and the average life curves. So, this is basically, based on the historical studies, right? And where they, observe the mortality patterns of, group of or similar equipments, and then they prepare or, the form, the survival curves, and, from the survival curve, you can help, the average life of the machinery at any point of time in their lifespan. Now, the next, so this is all about, the life cycle analysis, the life cycle, the benefits, the purpose, and what is the its perspective or use in the plant and machinery valuation. So that is what we discussed so far. More about the concept of a life cycle analysis. One of the critical important part of any life cycle analysis of any plant and machinery equipment is the depreciation, right? How it will depreciate over its useful life. Many assets depreciate early in their lifespan. Many assets have a steady depreciation over the years, and many assets have a less depreciation in initial year, but more depreciation in the remaining years. So depreciation is one of the important factors in life cycle analysis of any plant and machinery equipment. If we say that the depreciation, what it means. So in valuation, depreciation is a loss in value from all the courses. It includes the physical depreciation or physical deterioration. Then the second, is the functional obsolescence, and third is the economic obsolescence. So basically, we divide depreciation in three parts. One is a physical, right, which is due to its wear and tear or physical use, right? The second is the functional obsolescence, right? And the third is the economic obsolescence. Again, this depreciation, has again two more, part. It is one is the curable and second is the incurable. The curable depreciation can be calculated, by cost to cure, while incurable depreciation typically, estimate the percentage to, allow us the loss in value that is not economically, viable to, or, not economically curable, right? But broadly, if we divide the depreciation, the cause, it is mainly the three, cause: the physical, deterioration, the functional obsolescence, and the economic obsolescence. Now, when we talk, about the physical, depreciation, so it's a loss in value or, the utility or, the usefulness of the machinery because of its use, and it is mainly, this loss or in the value or, the usefulness is caused mainly by the wear and tear, right? Or sometimes it is exposed to, various, elements of, physical stress or other, the temperature or external, environments also, right? Which, reduces, its performance, right? So basically it's a loss in utility. It may be, result of exposure to the natural elements or the process area environment. It can be internal defects, many times, it can be due to vibration or operating stress or many other factors which can have a, impact on its utility, right? So that is the physical depreciation. The second form of the depreciation, right? It is a functional obsolescence. It's a loss in a value or in a utility of a machinery and a equipment, which is caused by, the inefficiency or inadequacies of the machinery itself when it's compared to the more efficient or a less costly, replacement machinery. So many times, because of, the technical advancement, right? We can see the newer machines are more efficient. They consume less power, right? Or sometimes they, produce more, components. So the existing machinery, it is in terms of the new machinery is inferior because of, if it is using more power, right? Then, it creating a more, operational cost, right? As compared to the newer machinery. And if it's it may be, less productive, right? Because the newer machine can produce, say, for example, a newer machine can produce 1,000 units in 1 minute. Maybe the existing or old machine is producing only 700 or 800 units per minute. So it is basically lost in the value because of its the function or the performance of the machinery, or sometimes if it has a higher operating cost as compared to the the new equipment, or in times if there is a specialized machinery, there are some techniques available where to reproduce those kind of equipment or specialized structure, there are less capital costs are involved, right? So all these are basically need to be adjusted or reflected in our depreciation calculation when we do or deduct the depreciation from the current replacement cost. The third the factor or the form of depreciation is the economic obsolescence. Now this economic obsolescence, basically it's a loss in value which is caused by the factors which are external to the machinery and equipment. So if you look at the other two forms of depreciation, which are physical or a functional, which are more due to or internal to the the machinery, maybe it's a because of wear and tear, it is not which are internal to the or inherent to the plant machinery, or some kind of a functional obsolescence. Again, it is it is internal to the plant and machinery, and it is not impacted by the other factors, while the economic obsolescence are beyond or caused mainly because of the some external factors, right? Now this external factors can be many. It can be availability of financing, right? It can be there is a loss of material, or the lower labor shortage, right? Or some kind of the regulation or law which has passed in a recent time, which restricts the utilization of or use of the existing machinery, right? Although this can be used, it has a balanced useful life, but because of the legislation or some kind of a change in the law, we cannot use. Sometimes there are some machinery which needs some kind of or some kind of a plant where the raw material cost has increased a lot, or labor cost has increased a lot, and it practically becomes unviable to use that plant, right, at that location. Or or sometimes there is a reduced demand for the product. Suddenly there is a new product has come in the market, and the product which is produced by the plant and machinery is no more on that in that much demand which it can produce, or there are some kind of a inflation high. So there are many factors which are beyond the or external to the machinery and equipment, right? But ultimately all these external factors reduce the utility, economic benefits associated with the machinery, right? And that is the reason it has to be deducted when we do the valuation. So these are the three forms. Normally depreciation immediately it comes to physical depreciation immediately comes to our mind, but the functional economic, it is equally important when we do a valuation, because that will have a big impact on the plant and machinery valuation. Now we discuss about forms of the depreciation. When we do a valuation or plant and machinery evaluation, there are many depreciation methods we used, and every method has a different purpose, and every method has a different impact on the, the valuation. One of the simplest method, normally which we use is, the straight line method. Then there are some other method like sum of year, digit method, unit of production method, which is directly linked, as the name suggests, to the production done by the machinery or the utilization level. There is one more method called Iowa curve, which follows the Iowa curve depreciation, percentage. Total use method, how much is, the utilization level of the machinery, based on which, we deduct the depreciation. Direct real or, dollar method, we say, show to depreciation method, where, depreciation is, initially high, then it is, going low, and then after, certain overhaul again, there is a better life, long life of the machinery, right? So, and there is a double declining balance method, which is, we call it accelerated depreciation method, where, sometimes initial year the depreciation rate is high, and, during the initial years of the, the life cycle, and the less at the, end of the life cycle. So these are the depreciation methods normally, we use, in our calculation. Now, when we do, or, calculate the depreciation, we come across different, terminology, right? Basically, all is related to the life, because, mostly all the depreciation methods, they, use the life or usage of, when they calculate the depreciation amount. So the first is the useful life. So useful life of a machinery and equipment is dependent on the type and the usage of the subject asset. The useful life may be influenced by evolving technology factors, environmental issues, operating cost, or availability of spares, or, technical expertise and market factors. So, for example, the computer has a very short useful life, say 5 years, due to, there are always, technology is changing, and, better and better, products are available at the same price or a lesser price, right? So that is the reason the normal useful life of the computer or any electronic or, equipment, what we have seen, they have a shorter useful life. They can be, sometimes we have seen that computers, or they have a more physical life, but, again, when better products are available, people try to replace it with the newer products to, keep for the better productivity, or the utilization. While at the same time, if we see a traditional, plant and machinery like, or workshop machinery like lathe, that has a longer useful life, right? Maybe 20, 25 years. So, so when, the idea is to, the detailed studies of, different kind of assets, needs to be done by the valuer, right? When they like to estimate, the duration of the useful life of the plant and machinery. And that is, one of the factor, what methods they need, use in the valuation process. Now, the similar or, related term is, the normal useful life. When we say a normal useful life, it's a basically, physical life, right? Or a physical life of the machinery, which normally, estimated in terms of years, or sometimes, units, that a machinery or, equipment will actually be used, before it is retiring from the service. So, the best evidence, if of the normal useful life is a statistical or some kind of actuarial data from the study, that is the best way where, similar assets or subject under similar operating condition, how much it has, been used, during, in terms of years. So an asset's useful life may be longer than its economic life, because owner may elect not to retire the asset from the service upon its expiration of the asset's theoretical economic life. So, for example, there is a tower crane, right? Now the owner has a same tower crane operational for the since last 10 years. Now earlier also they retired the tower cranes after 20 years of service life. So in this case of the normal useful life of the tower cranes would be the 20 years, because we have a historical or statistical data, right, based on our past experience or past utilization of the similar assets, that normally it has been used for the 20 years. So certainly if I have a cranes which is operational for the last 10 years, I can run this for the next year, subject to whatever regular maintenance needs to be done, or subject to I'm operating in the similar conditions. So basically, the normal useful life as compared to useful life, it is more depends on the physical nature of the or it's basically a physical life, right? Yeah. The third term is the remaining useful life. Remaining useful life is the estimated period during which a machinery and equipment of a certain effective age is expected to be used before it's retired from its services. So remaining useful life is basically the balanced life of the machinery for which we can use for the purpose it has been procured, or for the purpose it has been built, right? So the remaining useful life can be estimated or calculated by deducting effective age of the machinery from its normal useful life. So as we discussed earlier, we know that from the past experience or past records, we have seen that normally the tower cranes run for the 20 years, right? And they are normally retired on an average after the 20 years of life, right? So its normal useful life would be 20 years. Now we know that right now the crane which we have, or the subject crane which we have, the effective age of the crane is say 13 years, right? And if we want to calculate the remaining, or how long I can use the tower crane now, so it would be we know that normal useful life is say 20 years and the effective age is 13 years. So I can use the 7 years or the remaining useful life for the next 7 years. And now physical life, it is very similar to the normal useful life what we discussed. Physical life is the estimated period of time, usually stated in number of years, that a new equipment will physically endure before it deteriorates or fatigues to unusable condition, purely from the physical causes. So so it is more talking about the physical life of the machinery without considering the possible retirement due to say a functional obsolescence or economic obsolescence, right? So maybe if we take a so in this we are the physical depreciation factor, no economic or functional obsolescence in this life estimation. So physical life of the tower crane maybe for example it can be 25 years, right? While the normal useful life of the tower crane is set 20 years, because after if 20 years, if I have to use it for more 5 years, there can be, more, expense or some kind of a, cost needs to be incurred, which, doesn't make economically viable, right? So basically the physical life would be, looking at the depreciation or deterioration from the physical causes without considering the functional or economic factors in. Again, there is one terminology normally, we come across when we do, the machinery equipment valuation is the economic life, right? Economic life is, how long it is anticipated, that the asset could generate financial returns or provide a non-financial benefits in its current use, right? Now, there can be some assets which can generate direct, financial returns, which are mainly, we can say, they are part of the production, right? And there are some assets which are support equipments or, ancillary assets, which we certainly we need, right? But they are not involved directly in the production, right? Or they are not directly creating any financial benefits, but there needs to be there, to run the plant or run the show, right? So economic life is the how long it is anticipated that the asset could generate financial returns or provide a non-financial benefit in its current use. Now, in travel plane examples, we discussed earlier. Let's assume a scenario, right? Say normally, physically, say it can run for 25 years. The normal useful life is say 20 years, right? And so that is the two things. And now we have an existing subject crane, which is say 17 years old, right? Now, there is a requirement to, replace the mast of the tower, and certainly that is a very critical component which needs a huge investment, right? And, now I have a choice, if I, invest that much money, right, to extend its, life, or, I invest, where there is a new crane is available, where, it is more efficient and more economical than the older version. So I may choose given the my, economic analysis or viability analysis. If I feel that it is better to, retire this crane, right, and bring new, more efficient crane, certainly then, the economic useful life of the existing tower crane would be 17 years. Because although it can run for 25 years physically, or, based on past data, the normal useful life of the crane was 20 years, but after 70 years, I don't think it is economically viable for me to, run this crane for next 3 years after making such a huge, capex or investments. So I would retire it at this, age was, 17 years. So basically, I know that 3 years of, reduction in the usefulness, right? It is because of the economical factors, right? And that is where economical obsolescence may come into the picture, right? So this is what economic life, because, so all these lives are different. Physical life is the longest life. Useful life would be the lesser life. And the economic life can be less than the useful life, given, the economic conditions under which that machinery operates. Now, we talked about the depreciation, what kind of depreciation or forms of depreciation normally we used, right? what are the different methods of depreciation we discussed. We are going to discuss more in detail, the methods in the later, slides. We also discussed different definitions of the life, or different definition we used in, our depreciation calculation. There is one more, the concept, or the, I would say the tables we use, right? It's a depreciation schedule or chart, which normally, we prepare based on the past track record, right? And that help normally, the businesses to keep track of, long-term assets and give look or get idea how it will depreciate over the time. So basically, this schedule or tables, help us understand, how my assets are depreciated over the years. It is higher depreciation in the initial years, or higher depreciation in the mid life cycle of the years. So all this depreciation expense or depreciation reserves which we create, right? This can be, estimated using this depreciation schedules. So a depreciation schedule or chart helps business keep the track of long-term assets, give a look at how they will depreciate over time. It calculates an asset depreciation expense based on the date of purchase, initial cost, useful life, right? And track beginning and ending accumulated depreciation and the value of assets when it is replaced. So these are the benefits of the preparing or using the depreciation schedules. Normally, when we prepare a depreciation schedule, right, we have seen the, what are the things which are covered in the schedule or tables. So it would be, description of the asset, when it was purchased, the date of purchase, what was the initial cost, what is the estimated expected life we have taken in the depreciation, the method of depreciation. If there is any salvage value at the end of use, we can mention the salvage value. If we have already started the depreciation, what is the current year depreciation? If it's older assets, what is the cumulative depreciation? And after cumulative depreciation, what is the net book value? What is the depreciated value of the assets? So these are the 8, items normally, are covered in a depreciation schedules or table. So if I say, when we get a fixed asset register, you will see similar kind of, details. So when we go for, any asset valuation, exercise, we normally ask for the fixed asset register, right? And in that fixed asset register, we cover all this information, or we ask them to provide asset register with all this information. So we know, so this is purely, accounting purpose, so mainly it covers, I think one of the item I think we ask for is the quantity of the assets also, right? Now, we all discussed briefly, the depreciation, the methods, normally we used, right? The one of the methods which, we come across regularly or we use regularly is, the straight line method and the unit of production method. And these are, normally, if the machines are used, in a continuous products plant, or the machines are used, for a certain, regular period of time, these are the most appropriate, right? And many times, these are used for the accounting purpose, or, the tax purpose also. So many times, unit of production, lot of time we have seen that, the plants are not utilized fully, right? And, they are not or operating at a, full capacity, right? So we can use the unit of production method in those cases where, we know how much units it's procured or how many hours it has run, or right. And we can depreciate, from the replacement value or the, the purchase price, as per the, utilization level or the production. And there are, other depreciation methods which are, used, right? These are, a double declining method and sum of years digits method. Now, these are, we call it, accelerated depreciation method, right? Because in these methods, if we use these methods, see, large portion of expense or depreciation happens in the initial years, right? And, many, time, these are more used for the tax purposes because you have a initial year, you have a higher depreciation that will have a lower net profit or a net income, and that will lead to a lower taxes, right? So many times we have seen these are methods are more used for the tax purposes, right? By the firms or accounting firms. This also allows startups, businesses with a lot of bills to look up their costs sooner, right? And so that is also one of the the benefit of using this method. Now, if we go furthermore, deep into the straight line, depreciation. In this technique, the depreciation is determined by the subtracting a fixed percentage, right, from the current replacement cost new for each year. So, and again, in this straight line depreciation, the depreciation amount remained the same irrespective of, what is the age, or what is the age cycle of the machinery. And therefore, the estimated useful life of machinery, first we need to, determine. The current replacement cost after deducting the, the residual or a scrap value is divided by the assumed useful life. So, and usually the residual or a scrap value will be taken as a minor percentage of a, current replacement cost new. However, if, we can get a market data or some kind of a comparable for the residual value or a scrap value from the market also. So it depends. If you have a actual data, you can use the same, right? Or, you can, use some kind of a percentage, to estimate the residual or a scrap value. So this is, a basic, a calculation how, the straight line depreciation works. So, in straight line, depreciation, if we take an example of, say, there is a machine which is a 5-year-old, right? And say, it has a useful life of, say, 10 years, right? And if we assume, say, residual value or a scrap value is a 5% of, current new replacement cost, right? Then, the depreciation percentage per year comes around 9.5%. So that is, the 100% is the minus 5%, is the, the residual value divided by the total number of years, which will give, the depreciation percentage per annum. So in this table, we can see that, every year the depreciation percentage remains the same, or every year the depreciation amount remains the same, right? So, we are deducting 950 riyals every year, right, from the net book value. So accumulated depreciation would be 950 plus 950 plus 950 as the, the year goes. But the broadly, if we see the depreciation amount every year, it remains the same. It remains the 950. So straight line method, it's a very, straightforward method. Normally, used where, the machinery are, utilized, without any, say utilization level is, similar. There is no, so for example, a lathe machine, which is say designed to run for 8 hours a day, right? And if it is, used 8 hours a day, we can use a straight line depreciation method, right? Because it is going to have a 10 years of or 15 years of life, and physical wear and tear will remain the same throughout every year, because we are utilizing 8 hours a day. Now, when we have this kind of a table in place, and we have and one of the benefit of preparing this table, is to, use this depreciation percentage. If you see, the fourth column, so if we have a different lathe machine, right, which are procured at a different point of time, and we want to, deduct the depreciation, we can directly apply these factors or depreciation percentage, and accordingly we can, estimate the book value. Now, the other method, is the reducing or, diminishing balance method of depreciation, right? Now, this is another kind of a, depreciation, and mainly used when, asset has a higher utility productivity at the start of its useful life, and, later, less utility at the end of its useful life. So, due to which, depreciation expense that reflect, assets productivity, functionality, and capacity to generate revenue. So basically, this method will be used where, the depreciation would be higher in the initial years and less at the later, years of the, useful life. And basically, the calculation is based on current year's, balance being valued. Therefore, depreciation percentage is not same for the entire, useful life. Now, to, there is this one, simple calculation we have seen, put here just to understand, how, this, depreciation can be calculated, right? So, just, let's assume a case, right, where there is a 3-year-old mobile phone, right, we have, which has a, say, useful life of 5 years, right? And, there is a residual or scrap value, say 2% of the current new replacement cost, right? In this case, let's assume that, the mobile phone, or the current replacement cost new of the mobile phone is 5,000 riyal, right? Then the, the calculation is, how to, calculate the depreciation at the age of 3. So it would be 1 minus scrap value divided by the new replacement cost to the factor of age divided by, useful life. So, the depreciation factor comes is the 0.9, or we can say, 90% is the depreciation for the mobile, right? So, if we see, the depreciation percentage or the, the book value, right? It is higher, in the initial years. So if we see, in the first year, the value is, reduced by more than 50% in this case. So if I say similar to, say, a straight line depreciation, where, the initial depreciation was only a 10% for a 10-year of life. If we say, it's a 5-year of life, then it would be 20 years. In that comparison, so even in this case, if we use the straight line depreciation, the depreciation percentage would be 20% in the first year, while it is 54%, right? In diminishing balance, depreciation. So this shows that in the whole value is depreciated in first 3 years or first 2 years, and remaining 2 or 3 years there is a less depreciation. So this is the key difference. And if you see the value of the mobile phone, certainly we know the initial depreciation of any electronic machine would be high as compared to the later years. So these are the methods mostly more used for where there are more technical advancement in the machinery, or the technology is changing very fast for similar kind of assets. We can use this kind of a depreciation method. Mostly normally what we have seen, like electronic equipments or some kind of furniture fixtures, all these things, although they will have a more physical life, but in terms of value, the value depreciation would be higher in the initial years as compared to the later years. And that is where we will use this method. While the straight line method would be more preferred, where the utilization level of the asset is not similar every year. There is not too much of technical advancement on those kind of machinery, or there are not too much of economic obsolescence in those kind of asset class. So so every depreciation method has a different advantage, disadvantage, depending upon what kind of equipment we are going or we are valuing. Actually it should reflect at the end of the true value of the asset after the depreciation. Yeah, there is one more, method again, it's a sum of the year, digits depreciation, SYD depreciation method, right? Again, it is similar to, declining balance, SYD method treats an asset more useful in the earlier life by raising depreciation in the early years. So it is basically falls under, accelerated depreciation methods, right? So basically, most of the depreciation happens, in the earlier years. So SYD, depreciation calculation, is, like we need to see this remains the same, like initial cost minus salvage value. Depreciation are always, calculated. So from, initial cost minus salvage value, right? Then we have a remaining useful life and the sum of year of digits. Now this, here there is a catch here. If we go to the straight line depreciation method, we use the total useful life, right, in the denominator, right? While in sum of the year digits, we make the sum of the years. So if, for example, if there is an asset which has a 5 years of useful life, then the denominator which equals to 1 plus 2 plus 3 plus 4 plus 5, so denominator becomes 15. If it is the case of say straight line, the denominator will remain 5, but here there is a difference, right? Here the denominator is 15, right? So which is the sum of years, and that is what the name suggests, the sum of year digits. So, and we are assuming say 1,000 real is the say the salvage value or resident value, and the say initial cost is say 11,000 real. Then the below table shows how it is calculated. So the first year would be 5 divided by 15, so 33% is the factor. The second would be 4 divided by 15, so 26%. Third year would be 20%. Fourth year would be 13%, and the fifth year would be 6%. So if even in this method, the initial depreciation rate is very high. It's 33%, then 26%, then 20%, then 30%, and then 6%. If we compare it with the the diminishing balance method, the first year depreciation percentage was 54% as compared to 33%, right? The second year depreciation method was 80%, while in this method it is 26%. So although initial depreciation is high, the rate of depreciation in some of the years digit is less as compared to the declining balance method or diminishing balance method. Although this both methods falls under accelerated depreciation methods, which are basically high depreciation in the initial years and the low depreciation or less depreciation in the later years, but still the rate of depreciation differs in both the methods. We need to see how and basically it depends how assets are utilized or how value is depreciated for a different kind of assets over its life span or in its service life. So the application of different methods depend upon its utilization level, how they are going to use in their entire useful life. Now double declining method, again it is accelerated depreciation method. This is a third method which is part of this accelerated depreciation methods. But there is a catch here. There is a difference here, right? Yeah. So in earlier methods, we discussed, the depreciation rate changes every year, right? So if we go, in a diminishing balance method, we have seen, it's like 54, 79, 90, Then if we go to, this method, some of the year digits, it is 33, then 26, then 20, right? The rate of depreciation changes, right, every year. In this method, double declining balance method, although it's the accelerated depreciation method, the depreciation remains the constant. But there is a catch here. The depreciation is deducted from the book value, right? So here the example is given, right? See, there is an asset, for example, which has a 5 years of useful life, right? Say initial cost is say 11,000, right? Again, the salvage value remains 1,000, right? And depreciable cost, at the end, is 10,000. So annual depreciation would be around twice that say assume 20%, say 40%. So for an asset, say it's a useful life, say 5 years. If we see the beginning, say there is a initial cost, say 11,000. The depreciation rate is say 40%, right? Then the annual depreciation comes 4,400 real, and the book value comes to 6,600 real. Now the next year depreciation, the rate remains the same, but the base changes. We have to apply or deduct the depreciation from the net book value of the previous year, right? And so the previous year book value is the 6,600 real. Now we apply the 40% depreciation, which comes to 2,640, and the accumulated depreciation becomes 7,040. So the net book value is 3,960. So in this case also, although depreciation percentage remains same, the depreciation amount changes, right? So these are the different kind of the methods which falls under the accelerated depreciation methods, right? Yeah. Ruka, can we take a break for 10 minutes?
Yeah, sure. Before we take a break, let's just answer one question, one or two questions that I have. We have got a question from Mohammed. He's saying, thanks to the speaker, you mentioned a number of ways of depreciation methods. Is quantification using Rushton table still used in valuation reports as a method of measuring depreciation and obsolescence?
I could not understand what's a Rushton table still used in eval. So,
right, is saying easy quantification using Rushton table still used in valuation reports as a method of measuring depreciation and obsolescence.
see, if we have a historical data, right, for particular asset class, right, where there is a dual forms of depreciation has been captured in the depreciation table, then we can have a use. See, that is the one of the reason we use the survival curves, right? Because that is based on the historical data, right? But certainly this needs it's a valuer's judgment whether to when the value comes or whatever value comes, it really makes sense or it really the reflects the market condition or not, because not all the historical data will reflect the the future trend of the the value. So basically even today also we refer to historical data from the companies or anything, but certainly when we make our own calculation we consider a lot of other factors also. So blindly using in evaluation report, in my view we need to keep other factors also. Yeah, Ruka, you have a different view maybe?
Yeah, I think I really agree with you. The choice of any form of or a way of depreciation is the responsibility of the valuer. It's up to you to choose from the basket of depreciation methods, as long as you can justify yourself and give the reason why you are using that. And sometimes you have to take cognizance of the purpose of valuation and the basis of value as well in your assignment. So it can help you or lead you to any choice of your method of depreciation that you are going to use. That's what I can say.
I have well, one more question, like how many official ways of depreciation and based on what we can choose the appropriate. See, you need to understand when we do any evaluation, the depreciation has a three components, right? First is a physical wear and tear, right? Or physical depreciation. Second is a technical, obsolescence or a functional obsolescence. And third is a economic obsolescence. The depreciation method which normally we used is, it's for the physical depreciation, right? When we say a straight line depreciation, it's a physical depreciation. If, for example, there is a lathe, right? Now it is used for 8 hours a day in some kind of a workshop facility, which is manufacturing, say, automobile component. Now it is every day it is used, or every year it is used, normal use. The use is normal, 8 hours a day, right? Then for the physical depreciation purpose, let's go for, the straight line depreciation method, right? Here, we are not talking about the technical and the functional obsolescence. We are purely talking about what method we are going to use for the physical depreciation, right? So in this kind of a scenario, we can use a straight line depreciation method. Now there is a scenario, right, where the use or, is not regular. for example, say a generator sets, right, which is maybe used as a power backup, right? Or a generator set which is used on a site to supply the power to some kind of a ready mix plant or something. Now that is not used fully daily. Depending upon the requirement, it is maybe used for some hours or some period of time, right? Or it is generating some kind of a power units. So we can use unit of production method in those cases where the utilization levels are not regular. It depends upon the demand and the requirement of the user. So when we do a physical depreciation, we can have some other methods to be used. Maybe it can be a unit of production method or some kind of other method which can be appropriate fit to but they are more the talking about physical. There are some methods which we used here, which is like the accelerated depreciation method, right? Now, for example, in more electronic equipment, even if we say a mobile, right? Now, mobile, that can have a physical depreciation or a physical life of 5 years, but the value will not depreciate every year similarly. Initial year, it will have a higher depreciation. At a later year, it will have a the low depreciation. So, and because of that higher depreciation is not only because of the the physical nature, it is because of the technical reasons also, because there are new phones which are coming with a better technology, right? And that is the reason those kind of accelerated depreciation sometimes may indicate or cover the technical obsolescence factor also when we use that thing. So so there are different ways of depreciation methods. All these depreciation methods are mentioned in different study materials which we have referred. And the use of depreciation method, again, it's valuer's choice. What it is valuing, what kind of asset is it valuing, what market it caters, what is the utilization level, in which technological advancement, or what is the technical changes it is happening. See, we need to consider lot many things when we do a depreciation, right? Because when we talk of depreciation in plant and machinery valuation, it is not only a physical depreciation. So very difficult to give answer that is there any one method we can solve everything. It is not possible. So we need to keep consider many factors when we choose any depreciation method. It may possible when we have chosen any depreciation method, it only reflects the physical depreciation. We need to also consider the functional obsolescence or a technical obsolescence, and have to deduct some amount for that obsolescence also. So I think Mr. Mohammed has asked how many official ways of depreciation, and so Mr. Mohammed, we have covered so many ways of depreciation, right? And let me go back to my slide, right, which is 1 minute. Yeah, see, we have seen these are the different type of depreciation methods, right? And some of the methods are used for accounting purpose. Some of the methods are used for tax purpose also, to get the tax benefit also. And some of the methods are used for valuation purpose also, like straight line depreciation we use commonly, right? Unit of production method we use commonly. We can use Iowa curve, which we are going to discuss next. How we are going to this Iowa curve method, right? Like use total use method, again, that method normally we use if we have the data from the sites or production team, right? Observation method, yeah, it is in a limited special circumstances, and it requires a high skill to apply those kind of method, because it's a purely based on observation, right? So you should be very, very careful. And you should have a deep expertise when you use those kind of a methods, where you just see the machinery and say that the value depreciation is say 40%, or the depreciation rate is say 40%. So So yeah, these are the the methods which we we have mentioned in the training session, and all these methods are used for the different purposes. And all these methods we have referred different materials. So we have referred the ASM material also. We have referred Taqeem manual also. And from that we have collected all the information to give a broader idea, like how many kind of depreciation methods are available, right? And what is the impact on every year depreciation, and how it will have an impact in the value of the machinery. So there is one, question here. Must we state the method of depreciation? And definitely, we should mention, the more detail we mention in the report. I think we should mention the approach that the methods we use, the assumptions we use in value calculation. We should mention. Then there are some questions.
Right, there was a hand from Abdurrahman. Abdurrahman, do you still want to ask your question? Abdurrahman Al-Munai. I think he's no longer there. Okay, we can take a 10-minute break. Our time right now is 2:41. We'll be back at 2:50. We'll be back at 2:50. Thank you. Let's keep on logging in, and then we'll continue from there. Mr. Bravik, are you there? Mr. Bavik, are you there? Mr. Bavik?
Hi, Luca. Hi. Yeah.
That's fine.
Yeah. So yeah, just
Right,
let me.
Rasha, are you around? Rasha, are you back? Okay, thank you very much. Now we are entering our second session where we'll be continuing with our webinar. Over to you, Mr. Bavi.
Yeah. 1 minute. I'm just trying to share the screen. Just a minute. Okay.
Okay, whilst you are sharing your screen, I've got a question from Abdurrahman. Are you available? Are you around, Abdurrahman?
I think, Ruka, let's wait for a minute. Maybe, people are here and there.
Okay. Yeah, we can continue. Others will join us as we go. Abdurrahman, you can say your question.
Yeah. So yeah, welcome back, everyone.
Hold on, there is a question. Abdurrahman? I think he's not there. You can continue.
Yeah. So see, so what we discussed, the four, the major, the depreciation methods, right? That's the straight line which we normally commonly used, and the reducing balance method, the sum of your digits method, and the double declining method, right? Now, if we take the example of any asset, which has say, the cost of say, or replacement cost, say 1 million Saudi Riyal. And for the simplicity, let's assume that, the salvage value is 0 or there is no salvage value. And, let's take, the useful life 10 years. It's easy to understand, right? And if we use all the three methods, all the four methods, which we discussed earlier, right? If we see the depreciation over the years of, useful life, the graphs, it has, it has shown that, if we see the straight line, the depreciation is very straightforward. It is every year, it is the same. There is, no change, any in the depreciation every year. So it's a straight line. If we see other three methods, which are mainly, the accelerated depreciation methods, where, we can see the rate of depreciation or, the value depreciation is higher in the initial years, right? And less in the later years. So if we see the slope of the line, it is very, the slope is high for the other three methods in the initial year, and then it is becoming more flat in the later years. So this gives, the broad idea about how the depreciation rate works in a different, depreciation methods. Again, every equipment, will have a different pattern of, depreciation. If it's a lathe or workshop machinery, the depreciation would be different. If it's a power plant or cement plant, the rate of depreciation would be different. If there is a machinery which is, just supporting or ancillary equipment, not used continuously, the rate of depreciation would be different. So depending upon various factors, we need to choose which is the more appropriate depreciation method in our valuation exercise, right? Then comes the residual value of the machinery, right? So just to recap, we discussed the broad concept of life cycle analysis. Then we discussed more about the depreciation and the terms we normally use in the depreciation calculation. Then we use the different kinds of depreciation methods. What are the depreciation rates in the different kind of depreciation methods and in application, and the other terminology which we normally used in our working is the residual value, right? Now the residual value means the value remaining after the part of assets useful life or a complete useful life. So residual value can be or estimated in a different point of time. So if I want to know, say if there is a equipment which has for example 10 years of life, if I want to know what is the residual value after 5 years, maybe it is different. If I say what is the residual value after 10 years, it is different. So salvage value is different and a residual value is different. Salvage value is more referred to the end of use value, or when the assets are retired, what would be the value we will realize. But residual value is it depends at what age we want to have a estimation of the value. So so it also refer to the value of asset which is defined at a future point of time. So basically inversely proportional to the the useful life. So the more is the useful life, or the longer the lease period, lesser is the residual value, and the lesser is the useful life or lease period, higher the residual value. See now, what is the application of residual value? So see, many times, in many transactions, right, mainly for the leasing, this residual value is very important. So many times, a lessee, many leasing agreement or a transaction happens, where from the lessee perspective, residual value can be thought of as a value of asset at the end of lease term, and mostly it is based on the forecast of the future events. So residual value are critical component of any lease structure, because the primary objective of the lessor is to to receive an adequate return on the investment, to compensate for the cost of the funds and the inherent risk associated with the lease transaction. So residual value projections are used for determining assets end of use value for developing the rentals or lease rental, annual lease rentals. So if I understand with one example, let's say the bank has a issued a car on a lease, right? Car has a value of say 100,000. According to bank estimate, the car residual value at the end of say lease period is 45,000, right? So the lessee will pay the difference of the actual and the residual value, because the lease payments during that the period would be divided by number of years. So financial institution issuing the lease calculate the assets residual value at the time of lease agreement. The amount is usually fixed sum. It is determined based on the past model, future predictions. The residual value of lease is inversely proportional to the useful life. Higher the useful life, lower the residual value. Now, what can have an impact on the residual value? So it can the residual value or the factors affecting the residual life. It's a service life, use of asset, maintenance, market trends, future value. These are the factors affecting the residual value of the machinery. Now, how we estimate the residual value? So So, we understood, the residual value is the balance value at, any point of time during the, useful life or the life cycle of the machinery, right? But how to estimate? If somebody says that, equipment has, a 10 years of useful life, right? Now it's a 3-year-old equipment. What is its residual value? Or someone say, there is a equipment which is 7-year-old and or 8-year-old, and it's a useful life, say 10 years is the useful life. What is the residual value of a 8-year-old equipment? So there are two ways to estimate the residual value. One which we normally as a valuer we use is the second-hand asset approach. If I want to say estimate the residual value of say a crane or a genset which is say 5-year-old, right? And it has a say normal useful life of say, for simplicity, say 10 years, right? Then the one way is to I find the comparable in the market, right? I go and talk to the second-hand dealers, see if any transaction data is available. Then what is the or I make some kind of adjustments depending upon the year of manufacture, specification, make, model, and I estimate the residual value of a 5-year-old crane or a genset using a second-hand comparable method, right? So in this case, if I have some data where I can get a transaction or some kind of a listing where the asset is available for sale or it has been sold, then I can use that reference to estimate my residual value of my subject asset. So that's a one approach which is which normally we use like say in automobile or other which are available. The data are available from the market, or some cranes or some yellow equipments, right, which are general in purpose, traded in the market. Details are available from the second-hand dealers. So we can use those data points and estimate the residual value of the subject asset. Second approach again, is we use the depreciation tables, right? So we know, if we have a historical data where we have prepared the depreciation tables or the rate of the depreciation for the subject asset, like after 5 years, the rate of depreciation is 40 years, 40% or 60%. We can use those depreciation tables, or a rate of depreciation to estimate the loss in value or the the residual value of the the subject asset. So basically, we are using the depreciation tables or some kind of a depreciation method. After 5 years, this would be the residual value. So we have given two sets of example here, what we discussed earlier. So if I have a diesel generator set, right, and I want to estimate, its residual value after 5 years, right? Now, there is one way which we discussed, I go to the market, I talk to the dealers, I refer some database, try to gather, information about, if, where, at what price the data DG set is available, which is 5 years old in terms of, capacity, technical specific model, it is similar to the subject asset. Then, I can use those market data and estimate the residual value. Maybe, for example, it comes to around say 12,000, Saudi Riyal in our case. At the same time, I have a depreciation table from my historical records or from my database, and I have a rate of depreciation for each year, right, depending upon its use. So maybe in first year there was a say loss in value or depreciation is say 20%. In second year it's 10%, third year is say 10%, fourth year 10%, in the fifth year 10%. So I know the total depreciation is around 16,400, based on the tables I have, and I deduct from the current value 30,000, and the residual value would be around 12,000. So so this is also very close to what we got from the market. So these are the two ways again, it's a theoretical calculation, just to give you, the conceptual clarity. It might possible that, the difference can be a little bit wider also. So we need to make some adjustment, but these are the two ways, we can estimate the residual value. One is the market approach, and the second is the depreciation, methods, different kind of a rate or depreciation tables to, estimate the residual value. Yeah, so now so I think we covered majority of all the points which are related to the depreciation, right? Or we use, normally in our depreciation calculation. Now, the next point is, which is again an important, part of the life cycle analysis, this survival curves, right? Now, let me give you some, the background of the terminology, the survival curves. Now, the survival curves indicates the percentage of equipment surviving at ages ranges from 0 to maximum life. Now, it's basically a probability of, at equipment at different point of, its life period or life cycle. What is the probability of survival? The surviving property can also be expressed in numbers rather than percentage. However, the percentage expression is preferred because of its general nature. The purpose of constructing such curves is to analytically estimate the remaining useful life of the equipment. So a lot of these things or the curves are based on the historical, records or the performance of the equipment, right? Which can be, gathered, using the database, from the maintenance team or a production team who is maintaining it, who is replacing or, repairing the equipments. And basically the idea is to, whenever we do any depreciation calculation, one of the important thing which, we need to estimate is the remaining useful life of the machinery. And this is where these curves can help us, because there is a historical records are available. There is a historical trend is available, which can give you some guidance, like what would be the remaining useful life of the equipment if, if it is the 5-year-old machine or if it is a 6-year-old machine. So, it is basically the, why we build these curves, basically it's to analytically estimate the remaining useful life of the equipment. Now, the basis of this life analysis or life estimation is to review the past records, right? And if past records or data are not, enough or limited, we can use some, mathematical application or some kind of a graph extension to give, in what direction, it will, lead. So basically, although, all the assets are installed in, similar place, or it is used for, similar use, but then, their life may, differ, or their useful life may differ, or service life may differ depending on the quality condition it's used. So this is a very, generic graph, we have given here, which on one side indicates the, the service age or number of years in the service, and, or service age of the machinery basically, and the Y or the vertical column indicates the, the surviving, the property surviving in the service. So it's basically indicating the probability. So the vertical column, the left side column indicates the probability of survival, and the horizontal, the axis or the numbers, indicates the age of, property or machinery. So there are many terms it is used: survival curves, probable life curves. Survival curves is the actual survival curves based on the historical, data available. Probability life curve, which is, what would be the balance, life of each, asset or property at a different point of time. What is the total probable life at this point of, time. So these are the basically, mathematical, calculation based on the, the past historical data. And this will give a, indication what would be the remaining useful life of any equipment. If it's a 3-year equipment, what would be the remaining useful life? If it's a 7-year equipment, what would be the remaining useful life? So these curves will help us understand, what would be the remaining useful life, and which is what, very important when we do any, valuation. And again, we use a depreciation or cost approach, to estimate the market value of any assets. One of the critical, factor or, data we estimate is the, the remaining useful life of the equipment. Now, historically, there are different types of curves have been developed. The names comes from the, who has developed the curves. So, the Iowa type curves, were developed by, the team of, Iowa University in USA. Then there is a variable distribution curves. There is one more curves, Gomez-Mackham curves, polynomial equation. See, all these are mathematical, a calculation, to be honest with you. But, the more commonly used or the, are the Iowa curves, and which are referred sometimes as a, survival curves also, right? Now, again, this every asset has a different pattern of depreciation, different, life cycle. So even Iowa type survival curves are also, there are different types or different shapes, right? Which will give you different estimate of the residual life. So Iowa type survival curves are based on the set of data collected for the purpose of statistically predicting future service expectancy of machinery or, assets. So basically, these are, I would say, analytically or statistically predicting the, future service life or a probability of the machinery, right? So and why we call it statistically, because it is purely based on the calculation. There is no professional judgment or adjustments are involved here. It is purely, they refer to some sample data. From that sample data, they have prepared the graph. They have extended the graph to the, maximum service life of the asset. And it's basically a theoretical, a calculation at the end of the day. The techniques used and methods applied are similar to those used by insurance industry. So in insurance industry, when they decide the insurance premium or lot of other things, they predict the human mortality rate, right? And that is what we do. Instead of human, here the assets are machinery, plant, right? But again, it is based on the historical records. And then from the historical records, we generate a trend or we generate a curve, right? And that curve will give you, indication at what point of time, what would be the expected life or remaining life of the asset. So, and if we see, there are 4 types of Iowa curves there. So there are many, but, if we see, broadly, there are 4 types. And, every curve has a different, application, I would say. So there is an O-type curve, there is an L-type curve. As the name suggests, the curve will have a shape similar to the alphabet name, right? So it's O-type curve, L-type curve, S-type curve, R-type curve. And this each, curve or, the family has a different retirement or, survival characteristics. So let's go one by one. So if we say, O-type curve, right? Now, these curves have a high retirement rate in the early years, right? Now, here the retirement rate, when we call it is, different from the depreciation rate. So, this is high retirement rate means, in many cases, we call it that there is a terminology called infant mortality, right? Now here, generally the rate of retirement decreases with the age, right? So in O-type curves, this represents the class of equipment where the surviving, chances are very, very less in the initial years, and then it increases at the later years. So usually O-type survival curves represent the life characteristics of intangible assets such as newspaper, subscriber list, or some contracts which are, they have a high, infant mortality, right? It is very unusual for O-type survival curve to be representative of physical. Sorry. So this type of curve, is more applicable to, intangible assets rather than the physical assets. So plant and machinery will fall under physical assets. So very less application of this type of a curve in, for plant and machinery valuation case. Then there is a L type of, survival curve. Now this curve indicates asset retirement before reaching its, average life. So there are, so see all these curves are, developed for a different set of, assets, and which is, behaving and operating in a different environment. So, see, there are some assets, which retire before its, average life. Maybe they are utilized more in the initial years, right? So the older group of products tend to give more service than the younger group of products. However, L-type survival curves can relatively high retirement rate. Many times this early retirement is caused by asset being exposed to, life termination causes unrelated to physical life. For instance, some kind of a obsolescence, technical obsolescence, change in the customer demand, or need for more capacity, or a productivity. So this curve represent a equipment or a class of equipment where they are removed from the service or retired from the service, not because of the physical life, but because of some other reasons. Can be a demand or some kind of a supply issue, and because of that, we need to retire those equipments, right? And that is the reason they have a lesser service life than the average life, right? Yeah, now another S type survival curves. These curves indicate retirement before and after average life to be approximately the same, which implies that product is exposed to typical competitive environment, right? So here it's it is basically there are many equipments which may retire before the average life. There are many equipments which retire after the average life. So this basically it reflects to the assets or the machinery which are exposed to more typical competitive environment. And the last that the Iowa curve or a type of Iowa curve is the R type survival curves. Now this curve indicates products where the retirement age is higher after the average life. Certain assets display this characteristic with minimum breakdown early in life but high maintenance later service well beyond the average life of them. So this represents, this curve, maybe, reflect to the assets where the assets have a lower maintenance, in initial years. And that is the reason, majority of the assets will, will retire, after its average life. But, there are more assets, which are, retiring after, its average life. The reason being, after certain age, there is a more maintenance requirement, which doesn't make it economically viable to use. And that's the reason once its average life is over, normally it is retired from the services. Now, when we say, all this, curves or, survival curves, basically these are, the theoretical, application, right? And this needs to be developed from the historical data, right? And there is a, different ways to, make these curves, right? See, so one is to, the construct the complete curve from the, machinery and equipment data. So, just to give you example, say, like, here, there is a Dubai taxi, is the government taxi services, right? Now they have a fleet of, say, 5,000 taxis. Now they have a historically data available that, say, a Toyota brand cars are, retired from the service, say after, 500,000 of the mileage, or maybe after, 5 years of service life. They have some kind of a historical data, say from, say, Hyundai, or say from other, American brand taxis, which are retired maybe early because of, they are required higher maintenance to run them for the next 5 years. So if they have a historical data available in their system or with their production or maintenance team, what they can do, they can make a complete survival curve. If I procured, say, a 20 taxis in first year, it survived 4 years of service life. After I procured 200 taxis, which, survived 5 years of service life, because those taxis were utilized differently. Those taxis were operated by different drivers. Those taxis were operated in different region. Due to all these multiple factors, every taxi will have a different, service life. But when we collect all this information, gather this on information, and put it in the graph form, it will give a curve which will indicate probability of survival of average life of, the car at certain point of age. So there is a one way is to construct the complete curve from the data available from the maintenance production team, right? Sometimes full data is not available. There are some assets which are, have a longer life, say 20 years, 15 years, and we have a data till only 10 years. So we can construct the curve using that partial data, and then we extend through different application and complete the curve for the remaining, period. That is one way. The third way is to, we try to match. So one way is to, the first is to use the full set of data and construct the own, customized curve. The second way is to have a partial data and extend it. The third is to, that we have the partial data, right? Or we have generated the partial curve, and then we try to match it with the standard Iowa curves, right? And see which, fits the base. So if there is a curve, which is, say, say there is a life of, say, I have a group of equipments which are ranging from, say, from 1 year age to, say, 20-year age. Now I have a service history till only 10 years, right? I can just try to map that, curve with the different type of L shape, R shape, O shape, S shape, so Iowa curves, and I try to map and fit, which, best, meet the curve or lines, right? So there is a mapping of, the partially developed curve with the existing standard curve available or developed by, the institutes. And fourth, which, should normally be avoided is a judgment basis, which may differ, which need a deep expertise, and, but sometimes can be used is a judgment basis on Iowa curve based on the knowledge of machinery. If you maybe a person who is operating similar set of equipment since last 20 years and he has a deep expertise of, or knowledge of the machinery, he can generate or prepare based on his own, past experience, this type of curve. Generally, the valuer has insufficient data for the first portion, right? To construct, the complete survival curves, we don't have enough information. Whenever we go, even if we are valuing the similar set of equipments which are procured or which has a different effective age, we do not have sufficient data to form our own, survival curves, right? And that is the lack of information is one of the challenge we faced when we do evaluation, right? So that is the reason, the second option. So there is that the second option again, is, we do not have enough tools or capability to generate or extend the curve if we have a partially data. And the most, the preferred, the last resort for us to, match the, use the standard curves, or we use our own judgment, right? So although there are 4 ways to, generate these curves, right? And I just want to give, the broader, idea about, this curves will see, idea is to, estimate the useful life of the machinery at a given point of time. And what should be, see, right now we are, referring to, different, tables where, we have been given that, the normal useful life of the machinery is say 10 years, 15 years. But how this, data has been developed. So all these are developed using the past historical records, right? And so the idea is to how to estimate the residual useful life, or sorry, the not residual, but balanced useful life of the machinery. So, one of the way is to, construct the curves, and from that curve, we come to know that, at this age, the remaining useful life of the asset is say 5 years or 10 years or 15 years. So, and that is where this curve help us as a valuer, to estimate the balance useful life, right? And out of 4, we are left with only the 2 options because of the limitation we discussed earlier. Now, with complete survival, large amount of information can be obtained. So see, there are many, it's a analytical information, right? And when we make a graph, there are many, other information will also come out of the analysis. So once is a retirement patents, right? Certainly, we discussed in the life cycle analysis, the budgeting or, the replacing, the assets at a certain point of time, or a future, plan of the procurement of the new equipment. If we know the retirement, patterns, certainly, we know very well in advance, when, or we can make a budget or some kind of a funds allowance that, at certain point of time, we need to procure these equipments because the survival curve suggests that certain equipments or certain portion of number of equipments will retire at this point of time. Maybe certain equipments will retire after 5 years of time. So this will help, this retirement pattern will help us budgeting process when we do a life cycle analysis. What is the average service life of the asset? When we do any life cycle analysis, certainly we need to have what is the useful life of assets, till what, this asset's going to give me a benefit, economic benefit, right? So that will also give me, what would be the average service life of the asset from this curves. Third curve, which we normally as a valuer, we use is the average, remaining life. So we always, once we use a cost approach, right, we always need to estimate the remaining life. So normally, there are 2 ways to do it. One is, you have a effective age and the total life, or you have an average service life of the machinery and you deduct age minus, you deduct age from the service life or total useful life, you get a remaining useful life. Or you have an effective age and from the Iowa curves or survival curves, you get the remaining average life of the machinery. One factor which is also very important, in our valuation is the condition percentage. We know what is the condition of the asset. asset, and certainly it will help us, making some kind of adjustments, if we want to make during our valuation process. So these are the benefits, once that curve is generated or prepared. This can also give this other information which can help us in our life cycle analysis or our valuation. Now, earlier, we talked about survivor curves, right? Now, there is one more terminology called the life cycle curve. So life cycle curve, unlike survivor curves, they are curves, but they are function of time. And this shows, what would be the remaining service life of the asset, or remaining period of the remaining useful life. The life cycle curve is defined as a plot of anticipated percentage surviving, starting on the effective date of the assignment going. Basically, it's from the date or effective age of the machinery. For example, life cycle curve for a 4.5-year-old equipment is a portion of the survivor curve from the age 4.5 to the end. So we have carved out the portion, right? So the survivor curves may be, start from the age 0 till the, the maximum, the years any equipment has survived, right, or put in the service, right? But the life cycle curve is the portion of the, the curve, right, from the date of the, or effective age. So area under the, so the graph below, shows the survival curve for all the ages of the equipment, and resulting the life cycle curve for the 4.5 equipment, is, we have separated how would be the, life cycle curve for the equipment which is 4.5-year-old, right? And, the area under the life cycle curve divided by the starting point gives us, what is the remaining life of the 4.5-year, old machinery. So basically the use of all these, curves would be to estimate, what would be the remaining life of the machinery at certain point of time. Now, yeah. So, Ruka, before we, go to the case study, does anyone have any question?
Yes, we have a question. It reads, is not preferable to calculate depreciation in diesel generator example by working hours?
Yeah, see, if the gensets are used, for a particular period, and if we have a data, like, these gensets are designed to run for, say, 300,000 hours, then certainly we can use. See, I'm not talking about specifically for generator set, but for any equipment when we procure from the supplier, they give us, like what is the standard, normal or design life of the asset. So sometimes, say, when we procure a cement plant, normally the supplier of the, the cement plant, in their proposal, they will give a lot of technical details. Along with that, they will mention, the design life of the machinery or the plant is, say, 25 years, subject to it is run 300 days annually, and it is maintained as per the recommended maintenance procedure. So if we have that life available in terms of working hours, then we can use depreciation using working hours. So many times, so unit of production method, which we discussed earlier, right? is, it is the same thing which you are asking, Mr. Ahmad. Yeah, if we know the machine can produce, say, 5,000 units in its service life, and we have a data that, it has produced, say, only 3,000 units in last 10 years, we can use a unit of production method, 3,000 divided by, 5,000, which will give 60% of the depreciation. So, the first thing, if we want to have a DG sets depreciation based on working hours, then we should have its useful life in the same units from the supplier. Like this DG sets has been designed to run how many number of hours. Then certainly we can, use that. Yeah, Ruka, you want to add something? I saw some message here from on the.
No, it's okay. We can proceed.
Yeah, I think I lost the question screen. So is there any question someone can, maybe type again?
There are no questions at the moment. We can continue. I hope they will write as we go.
Yes, now I can see. Yes. Before we, start the case study, let me just, summarize what we discussed so far, right? So just to quickly summarize, the first portion, what we discussed is a broader concept of life cycle analysis, which starts from its investment phase, then its operational phase, and then the decommissioning phase. So investment phase talks more about the procurement, selecting the right kind of, technical specification, supplier, then, supplying the equipment, installing the equipment. That would be the initial or investment phase of the equipment, where, before we put to use, what are the investments and what is the, the analysis or, we do. So that is one thing. Then the second thing was the operational cost analysis during its, service life, which includes the operation cost, maintenance cost, some kind of a proactive maintenance requirement. And the third was the decommissioning or retirement of the equipment, and what are the factors we consider when, we retire those equipment, be it, complying with, any, local regulation or some end of service, liabilities. So that was more about the life cycle analysis phases. We discuss its benefit, what is the purpose. The main purpose is to, reduce the downtime, increase the productivity, reduce the cost, increase the service life, comply with the local, regulations or some kind of a, regulatory requirement. So that was the purpose of the whole, life cycle analysis. We went to the life cycle analysis valuation perspective, where, the life cycle analysis more focused on the service life of the equipment, depreciation over the, life of the equipment, and what is the depreciation and what is the impact on the valuation. All these things we discussed on a life cycle analysis. Then we went to the different kind of depreciation methods, which are the different kind of methods we use or need come across. It can be for the valuation purpose, accounting purpose, tax purpose. We discussed different valuation methods. Post that methods, we discussed the terminology we use in a depreciation calculation, which is useful life, normal useful life, economic life, balanced useful life. So all these different terminologies we discussed. Post that, we discuss in detail what is the different depreciation methods we use normally. So we broadly use, straight line method, and then there is the second set of method, which is, accelerated depreciation methods. And we discussed, broadly 4 methods: that straight line method, double digit declining method, sum of year digits methods, right? And so we discussed the depreciation methods. We discussed the residual value, which is not the same as the salvage value. It's the value at a different point of time or a different age of the machinery, what is the use of residual value. Mostly it is used in the lease structure or on a financing purpose where we need to decide the annual rent or lease amount, right? We discussed the different ways to estimate the residual value. So we discussed more about mainly two methods. One is the second-hand market approach or comparable method, or second thing, we use the depreciation table. We have the data of the depreciation of the single asset historically, and we apply the same depreciation rate and estimate the residual value at a certain point of time. Yeah, and then after post that, we discuss about the life cycle curves or Iowa curves. The main purpose of this curves to estimate the residual life, the balance useful life of the asset based on the historical data available. So we create a curve, right, based on the historical data, right, and then from their curve we estimate the remaining useful life of the subject asset. We discuss four types of method to generate those curves. Right, one is to have a complete set of historical data, and from that complete set we create our own customized survivor curves. That is one way. Second way, we discuss the partially available data and we use the mathematical tools or some quantitative methods to extend those graphs or curves. We third use the part data, we map it with the standard Iowa curves, and the fourth one is the pure judgment approach where based on our own experience we generate our survivor curves. But as a valuer, we I have a limited information to prepare those of type of curves, right? So we mainly depend on the Iowa curves or some kind of depend upon the professional judgment curves which we build over a period of time. So this is what we discuss right now. Now how to make these curves, right? We'll take a simple case study, right? Because so we have taken two case study here, right? One is very simple, just understand the concept. We have taken a very simple equipment. It's a telephone station equipment, right? Which normally, we see in our conference room, or in a meeting rooms, right? So it's a telephone station equipment, which normally connect to the normal and basically used for the voice communication. We have taken one sample, specification. It's a Cisco, a conference station module with the model number CP, 76. And these are the specifications. The purpose of this case study is to estimate the average life of the telephone station equipment, right? And now for a better clarity, we have taken two scenarios. If I go back to this graph, this graph is generated for number of equipments for almost lifespan of 27 years, right? But difficult to immediately jump onto creating this kind of survivor curve. So we have taken a very simple curve. How this curve has been made, that we will learn. Yeah, so if we take a scenario one, right? And what scenario one says, it's a hypothetical scenario. We have a 2 telephone units which are placed into service in the same time, right? So the first telephone was used for only 5 years, or it was put out of the service after 5 years, and the second unit lasted for 12 years. If I have only two data sets, right, and if I want to estimate what would be the average service life of a telephone unit from these two data bits, it would be 8.5 years, right? So after 3 years of service, for example, the telephone unit will have a 2 years of remaining life, right? And the second unit will have a 9 years of remaining life. So average remaining life would be 5.5 years. So here from this two, telephone unit, data, first we got an average life of 8.5 years. It is basically 5 plus 12 divided by 2, which will give you 8.5. At the same time, it will give me, what would be the remaining average life if I want to estimate, then, it is 2 years for the first set and 9 years for the remaining set. But what would be the average remaining life? It would be 5.5 years. So if I need to make, this, curves, see the first unit, so that both the units have survived for 5 years. So if you go to the curve, right, after, so if I want to, calculate the average service life, that can be calculated by, the area under the survivor curves, right? And the area under the survivor curve is 17 units, because one, telephone curve, telephone unit which survived 12 years, and the other telephone unit which survived 5 years, the total becomes 17 years, right? And the average service life then, is total 17 divided by 2 number of units, so it becomes 8.5 years. Same way, we calculate the average remaining life, it would be, 5.5 years, right? So this is a simple example, easy to understand, and maybe, we will share the Excel, working of this post this presentation. So, you can understand how it is, the curve is prepared, right? So on the one side, there is a number of units, and on the other side, there is a years since replacement. So if you see the curve, the both units have survived for next 5 years. So for both the units, the line grows flat. And after that, only one unit has survived for remaining 7 years. So the curve has fallen down and come to the unit number 1. So this is the simplest, form of the survival curve for the 2 units. Now, as we add more and more units, the curve will become more linear than, or more. Now, there is one terminology which we discussed earlier, is the condition percentage, right? Now, the condition percentage in general terms is the future service compared to the total service, right? So if we see a mathematical or theory compared to the total service available from the particular group of assets, how much service is left? The complement of condition percentage is depreciation. So it is how much service has been expended, right? So if we refer to the above, the example, the condition percentage is say 3 years, right? Now, so let me see the questions. Yeah, there are 2 questions. Can we please share the slide? So definitely, we are going to share the Excel working which we have done for developing this curve, right?
Yeah, the Excel will be provided via the Kima.
Yeah, because,
The-
I would be just, explaining how the curve is prepared, right? So if you have some kind of a historical data available with you from your client, or you are managing any unit, you can generate this kind of a curve by your own. And based on that curve, you can estimate the remaining useful life of the asset or average service life of the assets, right? The idea is to develop this curve so we can estimate what is the average service life or useful life of the assets, or if once it is developed, we can estimate what would be the remaining life of the assets. So the first scenario was very simple. We just took two telephone units, right? One lasted for 5 years, second lasted for 12 years. Average life came to 8.5 years, right? Now, and the graph was very simple, straight. Now, if we take a second scenario where there are 100 telephone stations in one of the commercial building, right, which are placed in the service simultaneously, right? Now, every telephone station would be used differently by the different user in the same building, right? So some of the units will retire early, right? Or, and some will retire late depending upon its use. So we have created a pattern of retirement, which is present, which is shown in the graph. We can see, the retirement is, peak between 9 to 10 years, right? So if we see 80% of the units are retired in, 10 years of life. So I'm talking about the left graph, and there is a red, the line is shown, right? So the first dot shows the number of units put in the service. The left column in the horizontal axis sees the age in the number of years. So if we see the curve indicates that, the average, retirement or average service life is somewhere in the range of 9 to 10 years. So, and we have a sample data sets available where we have, put all the graphs. So here, the retirement frequency we have, put, so it's the inverse graph, right? First, the left side is the survival curves, the right side is the retirement frequency, and the retirement frequency is shown, the graph fixed at the 10 years or 9 years of age. So if you want to calculate the average service life, for, for the telephones, it would be area A plus B as shown in the, the graph, divided by number of total units. So this 645 unit years plus 205 unit years divided by 100 units, it will give you 8.5 years. So the average service life of the telephone unit will come to 8.5 years. Now, if I want to know what is the remaining life at a say 6 years of age, then it would be area B, which is the remaining life of the assets, divided by the surviving units, which are 73, right? So because if you map the line here, it will go about the 60. So around 73 is the, the surviving units. So 205 units here divided by 73 give you 2.8 years. See, all these are, mathematical calculation, and we have covered step by step in detail in our training material. So if anyone has any issue, let me know, or maybe we can throw some more light. And and the same is the condition percentage, or the depreciation percentage is average remaining life divided by average service life. So we calculated 2.8 years as the average remaining life, and the total average service life is 8.5 years. So depreciation percentage is 33%. So basically, the idea is to create a graph from the data available historically, right? And use those graphs for our future purpose to estimate the average service life and the remaining useful life at a certain point of time. So this is one kind of a scenario where, all the units are placed in service in one day or a day one, right? And then they survive differently. So some survive maybe 5 years, some survive maybe 10 years, some survive maybe 15 years, right? But all the units were placed in service on day one, right? And this can be applied to this kind of equipment where, in a commercial building, all the, units were put in use in the same day, right? But in real life, there are different scenarios, right? There can be, as I mentioned earlier, right? If there is a government taxi services, right, where, you place maybe 200, 300 taxi on day one. After 1 year, you added 100 more taxis, and you maybe retired, 10 or 20 taxis. Then after 3 years, you added one more 100 taxis, and you retired maybe, 50 taxis. So you keep adding new taxis in your fleet. You keep removing some, or retiring some taxis, because of many factors, and that going on every year. And then, the life cycle or survival call would be different, right? So the second case study which we have mentioned here, right, that is, discuss more about, say electric generator, right? And that is how, we have created, in this case, the gensets are put in a different point of time, right? Different quantities, and how to build their survival cost. Right, so it's a simple electric generator which normally, used as a power backup or to supply the power on the site. Right, we have taken, it's a 1250 kilowatt, capacity, a genset, right? And, and these are the technical specification. Right now, the idea is to how to estimate the service life of electrical generator, and we have taken, say, a 50 generator units which are put in place in the service at the same time, right? So here, it is the same. Again, we took the 50 electric generators, right? They were placed in the same year, same time, right? And, uh, based on their, survival, we created a one survival cows, right? It is the same way we started plotting, the curves on the Excel, and we got this, a trend of the survival curves. We also got the trend of retirement frequency. Again, here we can see the retirement is high in the 10 years, right? So all this information will help us, estimate, what is the average service life, what is the average remaining life of the unit. We will share the Excel working here, where, it would be clearly step by step, in our training material also it is mentioned how the graph would be created, right? Yeah, Ruka, I think,
Hello.
yeah, so we have finished from the presentation side.
Okay, that's fine. Thank you very much for the presentation. And we don't have any questions, and our time is almost there. So thank you very much, Mr. Bavik Vora, for your presentation. Thank you everyone for joining. See you in the next
Ruka,
webinar.
I think there is one more question from, engineer Mr. Abdullah. See,
Okay.
if there is a missing information, we discuss,
Oh,
need
yes,
to,
there's another question we are waiting.
yeah. So in this, just to, let me share the screen again.
He's saying if there is a missing information, how can I make assumptions? These are assumptions that are made when someone is working on the life cycle analysis. So he's making assumptions, and then what happens?
So, we discuss, not all the time, we have the data to create this kind of a graph, right? right? So that is the challenge we normally face, the limitation of the details availability, data available. So here we have mentioned that valuer has a insufficient data normally, right, for the first or second option.
Mhm.
So normally if we have part data, we should try to map, match the partial curve data to the standard iota curve data. So what happens if you have say you created a curve using whatever data sets available, but that curve is partly created, right? Now, for example, I discussed if there are the assets which normally run for say 25 years of life. Now you went to a site, right? The data sets are new. They are just only used for say 5 or 10 years of life. You don't have the 25 years of data set. The only way is to match that partially generated curve to the standard Iowa type curves. So the standard Iowa type curves are available, right? There are some theses available, and in which they have developed the standard Iowa curves for different type of assets. So for specific assets, they have created a curves, and you can use those curves, and try to match with the our curves which we have created based on our data. So that is the only way. Or the second way is to use our judgment.
Okay, that's fine. I hope has been answered. But in terms of assumptions, what are the assumptions, the basic assumptions that you should consider when you are making these kind of curves, survivor curves?
No, survival course, we really, the assumption would be whatever, the how we are using or, try to map, these are that is the fundamental assumption we take, that we have tried to map it with the, the S curve or O curve, certainly, it is not necessary that the curve which we have mapped, that will actually reflect, the actual service life of the machinery. So that's our assumption, right? That we assume that, this will use, or the average service life would be based on this mapping would be say 10 years or 20 years. So that's the base assumption we take. Maybe actually it can run for maybe 11 year or 9 year, right? But the fundamental assumption would be, whatever average service life we derived from this Iowa curves, we are taking that as a, in our valuation calculation.
Okay. I can see. Okay, he's asking, is that belong in general assumption?
See, I don't see all these curves are very specific to equipment. So it should be equipment bias. So we have to write equipment wise assumption, to be honest with you. There won't be any one curve which would be used for all the asset class. If you are only focusing on say one asset, one type of asset, then it can be a general. But if you are evaluating different type of assets, and if you got a different kind of Iowa curves, then certainly we have to write assumption, asset by asset. We cannot have a general assumptions. So
Does it differ with the different asset categories?
yeah, see, to be honest, when we write any assumption limitation, there are two sets of assumption limitation we mentioned in our report. One is a general where which is normally we assume because that doesn't fall under our duties. There is a standard assumptions we take of normal upkeeping, maintenance. We have not seen the equipment, or we have not opened the engine of the car to see the condition. So there are some standard assumptions. There are some specific assumption also we mentioned, and I think this would be the specific assumptions, because not for every asset class or asset type we will going to use the survival curves. Some some data we will use the standard life estimation available in our database, and for some of the asset we are going to use this curves where we have a historical trend available.
Okay, that's fine. Thank you very much. I think we no longer have any questions. We are done. Thank you everyone for joining. Thank you.
Yeah.